Hey everybody, so like Lavanya said, I'm a deep learning instructor here at Weights and Biases, and I'm also a graduate student at the University of California, Berkeley, studying the optimization of neural networks. And I thought I'd take some time to talk about a subject that is near and dear to my heart, and not many other people's, which is linear algebra. So linear algebra is something that's super critical for machine learning, but something that a lot of people kind of like dislike or try to, it's sort of like vegetables. Nobody wants to, eat their vegetables. They want the tasty steak. And part of the reason for that is that I think linear algebra is kind of taught the wrong way. It's taught as though it were like the algebra you learn before, where you learn things about addition and multiplication. You learn rules for combining those two things together to generate new symbols, new equations to solve for things. And when you take a linear algebra class, sometimes you spend the entire time on computations like that. How do I get the determinant? How do I get the eigenvalues? Things like that. And folks end up getting confused because the rules for linear algebra are very, very complicated for manipulating these symbols around, and they don't behave like algebra that that we learn when we're younger. But this is not the way that linear algebra has to be taught, and it's not the way linear algebra actually gets used in machine learning. And so one big example of this is that linear algebra frequently is used not as like solving systems of equations the way you would in a typical linear algebra class, but as sort of for geometric transformations. So in the bottom right, you can see an animation of some linear algebraic manipulations considered as geometric transformations. So this is from this YouTube series by YouTuber 3 Blue 1 Brown, aka Grant Sanderson, who is a really great mathematical educator on the internet. So this YouTube series sort of presents linear algebra as the study of transformations of spaces. And so it's a good one to look at if you want to, if you took one of those classic linear algebra classes, and find yourself doing deep learning but find that it's not taught you the linear algebra that you want. There's another one that's I think a lot of people have maybe heard of or seen that YouTube series before, but there's another one a little more avant-garde, graphical linear algebra. So this is a blog post series by this mathematician Pavel Sobczynski. And the idea there, the tagline is that linear algebra is what happens when adding meets copying. This one sort of a little bit different from the way things end up getting used in deep learning, but it has this really neat style of diagrammatic reasoning. Everything is done instead of using equations, but with pictures. And so this is done in a way that's entirely and completely rigorous, which is really impressive for pictures as opposed to equations. And so I found that it's something that can really sort of take your mathematical understanding of mathematics in general, but linear algebra in particular, up to another level. But I'm not going to present sort of either of those ways of thinking about linear algebra today. I'm going to talk about how linear algebra can be seen as something that's more like programming than it is like algebra. And in this view, we're going to see that matrices are our functions, shapes are our types, and multiplication is composition. I'm not going to have time to go through the entirety of this in just the like 20 minutes of this, but I'm hoping to give you a taste for how you can take some intuitions that you've built from working with computer programs that don't look like linear algebra to understand these linear algebra components of machine learning and deep learning much more deeply. So in programming, we combine functions that have matching types through function composition, and we use those to create programs. In linear algebra, we combine matrices with matching shapes through matrix multiplication, and we use those to create more matrices. So this is the style of programming that I'm thinking about here. Isn't the sort of object-oriented programming. I'm thinking about strictly typed programming, functional programming in particular, for folks who are familiar with the different types of programming languages that are out there. But just in general, there's connections with just the way that we think about our computer programs, no matter what paradigm we're working in. So in all kinds of programming, we define one function, one program in terms of others. So if I wanted to check whether the string that I'm composing is too long to tweet, I might first get the length of that string in the number of characters, then check if that number of characters is over 140. So that's what the Python function on the top there does. And it's calling this function over 140 that checks whether its input, which is a number, is above 140. So, this is, we want to take this, this piece of logic about too long to tweet and break it down into its constituent components. That first function, computing the length, I want to take us back a little bit to the sort of the way functions are sort of initially introduced in when you first learn about functions, at least in the American school system. So we draw the types, all the possible inputs the function could get on the left, and all of the possible outputs that the function could create on the right. So the len function takes in a string and outputs how many characters are in the string. So the string A has 1 letter in it, the string BB has 2 letters in it, and the Declaration of Independence has 8,007 characters in it. These arrows map what input goes to which output when this function is applied to them. I can do the same with that over 140 function. Now that over 140 function takes in the integer, takes in an integer, could be the integer output by the len function, and returns a Boolean. So it checks whether the number is over 140 and so too large to tweet. So all those strings A, B, 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 A, those are all under 140 characters. So over 140 outputs false. And so they're tweetable, but the Declaration of Independence is not. It's over 140 characters, and so it is too long to tweet. And so in order to build that too long to tweet function, I just follow those arrows one after another. So to get the length of the Declaration of Independence, I start there, and I follow first this red arrow, then this blue arrow. And by following those two things, I've essentially created an arrow that goes from this thing all the way on the left to strings all the way to Booleans on the right. And that is our too long to tweet function. So we've defined this too long to tweet function as the composition of two simpler functions. And so too long to tweet goes from strings to Booleans, where it's two pieces. Len goes from strings to ints, and over 140 goes from ints to bools. So I'm going over this in detail, in part because I want to make sure that we can carry our intuitions over from the world of programming over into the world of linear algebra. So as a first step, I just want to introduce the notation for how this would be written in mathematical terms. So on the right here, I have a sort of more programming way of writing it. So len is a function that takes strings and returns ints. And that would be written in mathematical notation. We'd name our function and then a colon, the type that comes in. So type A is generic here to type B, which would be ints. And then we can do the same with another function. It takes the same input as f outputs and returns this returns a different type, Booleans. If we wanted to denote the combination of these two functions, their composition, we write something that looks like this, G circle F. So my preferred way of pronouncing this is to say that this is after. So I apply G after F, which helps me remember that this symbol means that the function F comes first. And that's actually pretty important because when we combine functions, the order is super, super important. So Mani is already, his ears, or their ears have pricked up, given all this talk of composition. Indeed, this is going to turn out to be a category theory approach to linear algebra. So when we combine our functions, the order that we do this is super, super important. So if I do that, if I check whether a number is bigger than 140, after first checking the length of the string, that's very different from trying to check whether taking a number, determining whether it's over 140, and then asking for its length. you know, what does it mean to take the length of a number. In Python, that won't work. And so that's represented by the fact that this G guy here goes from B to C, and F goes from A to B. So if I give F a C, then it doesn't know what to do. So this is all relatively, it's like a core part of programming, that we make sure that the functions that we're applying know what to do with the stuff that comes into them. And so I want to sort of port that over to linear algebra by thinking about linear algebra as a combination of functions and not just as matrix multiplication. So in linear algebra, we have these linear algebraic equations that say that this matrix here on the left of the equal sign is equal to this matrix here on this combination of matrices on the right-hand side. So just as a very simple example, say the matrix Z is this 2-row, 3-column matrix here, and the matrices Y and X are these 2 columns here. So one way to interpret what this means is that if you follow the matrix multiplication rules and combine Y with X, you'll get the matrix Z, and that's fine. But I think a better way of thinking about it is that applying the matrix X to a vector, then applying the matrix Y to a vector, is the same as applying the matrix Z to a vector. So that's the same thing as saying that symbol F after G or G after F was the same as first applying F, then applying G. So what does that look like if we try and cast it, if we try and dig in a little bit more detail? So that function X, that matrix X there, can be thought of as a function. So we can write it in the same way as we wrote those other functions, the len and the over 140 function. We put its inputs, all of its possible inputs on the left. It's every array with 3 entries in it is on the left. And it outputs arrays with 2 entries in it. So these two, for this one, it just picks out the first 2 entries and throws out the third. So these 2 arrays get mapped to the same output, 0, 1. And these other arrays get mapped to 1, 1, 3 gets turned into 1, 1. And so we would denote that following that, following the sort of programming style syntax as saying X is a function that goes from arrays with 3 values to arrays with 2 values. And we write that a little bit more differently when we got to linear algebra, but the principles are all exactly the same. So if we were to write it in our mathematical notation, X is a function that goes from, now arrays with 3 elements are called real vectors in linear algebra. So these would be, essentially this is a floating point array with 3 entries in it, and returns a floating point array with 2 entries, or a 2-dimensional real vector, or people call it an element of R2. This is the same thing as when, for the class of linear transformations, to say that X goes from R3 to R2 is to say that X can be represented as some matrix. So as a matrix with 3 columns, so 1, 2, 3 columns, and 2 rows here. And so this function takes something that lives in like a 3-dimensional plane. So these are like our X, Y, and Z axes. So it lives in this 3-dimensional world, the inputs to X, and the outputs of X live in this 2-dimensional world. And because the outputs of X live in this 2-dimensional world, we can combine the matrix X with the matrix Y to get a single map, because the inputs to Y also live in this 2-dimensional world. So Y has 2 rows and 2 columns. So because it has 2 columns, its inputs live in a 2-dimensional world. And so we can combine it with the matrix X. And now, just like we could combine over 140 and len to create a single function, too long to tweet, we could combine these 2 matrices together to create a single matrix that goes from R3 to R2. So a single matrix that goes from 3 dimensions to 2 dimensions that does the same thing as first applying the X matrix and then applying the Y matrix. And The utility of this is that if we focus too much on just thinking of linear algebra as algebra, we can lose sight of the meaning of what we're doing. So when we're doing linear algebra, it always is the case that what we mean is that we've got these matrices that represent our functions, and we're trying to say, oh, this function is the same thing as this other implementation of this function, just as like 3 different steps. So z is the same thing as y after x. But if we think of it as algebra, we would think of it as, oh, z is equal to y times x. And then we'd suddenly be surprised to find out that yx is not the same as xy. Even though with regular numbers, that's the case. 2 times 3 is the same as 3 times 2, and that's true for any pair. But that's generally not true with matrices. And people find this really surprising. I found it surprising when I first learned linear algebra. I found linear algebra really confusing, unintuitive, and uninteresting. And it wasn't until I needed it to do deep learning and I came across this other way of thinking about it that I both understood why it was important and understood why this shouldn't be so surprising. Matrix multiplication is less like multiplying 2 numbers, and more like composing functions. And when we compose functions, the order is super important. Putting on my socks, then putting on my shoes is very, very different from putting on my shoes, then putting on my socks. And so that's something that just sort of gets missed out on when we think of linear algebra too algebraically, and not enough in this sort of like functional way, the way we think about our computer programs. So if we think of linear algebra as being about combining matrices with matching shapes through matrix multiplication, as being a sort of like special case of what we do in programming, where we combine functions with matching types through function composition, then I think we get a much deeper sort of understanding of what we're doing with our linear algebra. And I find this is actually, this isn't just a sort of mathematical curiosity, though it is, like beautiful and fun to think about. It's something that I remember and that you can remember when you're debugging or reading code that has a bunch of linear algebra in it. Follow the shapes the way you would follow the types in some other program. If you don't know what's going into the program and what's coming out of it, if you don't know how inside the program it's turning one shape or one type into another type, then it's much harder to understand the program. I'm always, when I'm debugging, tossing in print statements that print out the types of things. Is this a list? Is this a list of lists? What's going on here? And you can do the same thing with shapes when you're debugging your machine learning code. And something that can check shapes is as good a friend as something that can check types. So there's lots of machine learning frameworks out there that can check to make sure you're getting your shapes right. And it's as useful a thing to have around as something that can do your type checking for you when you're doing when you're programming with types. It's also useful for insight into a bunch of decomposition. So principal components analysis, QR decomposition, the singular value decomposition. I found them super mysterious when I first started thinking about them with linear algebra, because I wrote them down as these like big collections of numbers, these big equations, and tried to follow linear algebra rules to see what was happening. They're really something that's easy to understand once you think of them as ways to turn one matrix into multiple matrices, the same way we take code and we refactor it from one big pile of expressions into multiple subcomponent functions. And then lastly, this gives some insight into deep learning. If I change the entries in a matrix a tiny bit, just a little bit, like I add a small perturbation to one of the entries, I change the function it computes a little bit, right? It does almost the same thing, but does something slightly different. That's not at all true for a Python function. If I change one letter, it might crash. If I change a def into a dof, then dof's not a keyword and the whole thing falls apart. So this makes Python functions really hard to automatically optimize, but linear algebra really easy to optimize. So, and optimizing linear algebra was a big part of the sort of science and engineering feats of the 20th century. And it's also behind deep learning. Deep learning is essentially differentiable programming, or programming by optimization. And one of the most important parts of deep learning is that linear algebra gives a whole bunch of functions represented by matrices that are all differentiable, that are all optimizable. And so it helps us get to this point where we can write lots and lots of programs that we can optimize, that we can differentiate, and that can do all these crazy cool things like beat a game of Snake. So if I hope that this was interesting to folks, and if you found it interesting, the Essence of Linear Algebra series is a great place to start. It's, effectively bingeable, so you can do it in a single setting if you want. Graphical Linear Algebra, the blog series on the diagrammatic approach, is great for folks who'd really like to build their math chops. It's sort of aimed at folks who don't have a ton of math experience. Maybe they took math in high school, maybe a class on calculus in college, and maybe a linear algebra class, and that's it. So it's aimed at that folks, but it's aimed to present some really complex and difficult math to you in a way that's very reasonable and understandable. So I'd get so that's a strong recommendation. And then lastly, a plug for a series of YouTube lectures. So the general idea of thinking of as many things as possible in terms of compositions of functions, of combining things and then uncombining them into decompositions and breaking them apart. This is a sort of generic approach to lots and lots of branches of math. And there's some really great YouTube lectures aimed at folks who've had some experience with C++ and Java, maybe done some complicated programming there with things like, I don't know, like generics and parametric functions, I think is what they're called, that sort of present a lot of these, very abstract math ideas, but give these nice concrete examples from the world of programming. So that's Bartosz Milewski is the author of those, and he's a really great educator, and and he's presented lots of material. So that's all I have. It was a little fast. If you found it a little bit confusing, that's probably more on the speed at which it had to be presented than on you. So I definitely still check out those resources where you can take it in at your own pace. Feel free to email me if you have any questions. Check out my personal blog or my Twitter if you want to see some more stuff on this and other topics in the intersection of math and machine learning. All right, that's all I had. If anybody has any questions.
Cool. Thanks, Charles.